you all for being here attending this presentation. As Celine said, my name is Marco, and today I'm going to talk to you about my research as a PhD student that is summarized in this thesis called Nonlinear Elasticity in Concrete Structures, Toward in situ methods for integrity assessment. And perhaps the title of this presentation might sound a bit complex, but the essence of this work is on how the systematic evolution of elastic properties measured in situ concrete structures can give us meaningful information about their microstructural composition and how this information can be interpreted in terms of damage assessment or for integrity assessment purposes. The main tool that I use for this analysis is mechanical waves, and those are of different kinematic nature and different sizes. And I think this is a very good starting point, mechanical waves. Mechanical waves have been used for quite a long time to investigate the elastic properties of different materials. Properties like their stiffness and the internal composition can be inferred by analyzing the velocity at which such waves travel through the material and the energy that they are able to transport from the source to the receiver. Those are pieces of evidence that we can obtain to deduce that a piece of concrete is stiffer and more consolidated than a piece of soft wood. The linear elasticity theory dictates the mathematical and physical rules that we have to follow in order to reproduce numerically such a wave propagation phenomena. This linear elasticity theory assumes a linear relationship between the stress that waves induce to the material and the strain that we can measure as a response. One of the implications of using linear elasticity to describe wave propagation is that it doesn't matter how much we deform the material. It doesn't matter how much we stretch it or compress it. As long as such deformation is within the elastic regime of it, the velocity of wave propagation is not going to change. And that means that the elastic properties of the material will remain constant at every instance of the deformation. So this is like taking a picture on the elastic properties, and this picture will remain valid at every instance of the deformation. In the context of civil engineering, linear elasticity is the backbone of a set of techniques that use different features of mechanical waves to estimate or to identify damage in civil structures in a non-destructive manner. Naturally, those techniques are called wave field-based non-destructive testing techniques, or entities. And to give you an example in a nutshell on how this set of techniques use linear elasticity to identify damage, I'm going to take as an example ultrasound pulse velocity. So the ultrasound pulse velocity takes advantage of the velocity of the first wave train that travels from source to the receiver as a proxy for damage assessment. That means that high wave velocity refers to healthy material, and low wave velocity refers to degraded material. There are some things that we have to consider in order to use ultrasound pulse velocity for damage assessment. For example, that the induced waves, the waves that we induce to the material, must be in relation to the crack size. That means, the features of the waves have to be set up in relation to the crack size that is commonly unknown. And besides, the imperfection must be also in the way of the direct travel path. But then what happens with those small imperfections that are randomly spread or distributed in the material? So those small scale cracks essentially remain hidden to the conventional techniques. We cannot see them by using these conventional practices. And they are important indeed because those small imperfections are the prelude to large scale cracks via crack propagation process when the stress is concentrated in small microcracks. Then the research question of this work comes, can we find practical ways to use mechanical waves to assess the effect of small scale imperfections in concrete structures? Well, it looks like we can because, we can take advantage of one specific elastic feature of complex solids. So concrete as a composite material exhibit a more complex relationship between stress and strain than the one dictated by linear elasticity. Indeed, the elastic properties of concrete depend on the stress state, the stress at which the material is subjected to. And more interestingly, it also depends on the time when we measure such elastic properties. One classical example that we can consider to observe this stress dependency is that when we compress the material in very specific situations, we can observe that indeed the velocity of wave propagation tends to increase. And this increment as a function of stress is also referred to as the acoustoelastic effect. As you can observe, this effect tends to be linear as a function of the stress. And one typical example, well, typical to some extent, of this time dependency that is also called non-classical nonlinear elasticity is the so-called slow dynamics effect. Slow dynamics effect is essentially the material degradation or the degradation that elastic properties of the material suffer after the action of an external perturbation and the subsequent auto-healing process that happens through the time. So we can observe these hallmarks of this slow dynamic process, that is the softening, the material degradation, and then the subsequent auto-healing process that is called relaxation process. The important thing is that this process happens in very large time scales. Essentially it happens very slowly. Those effects are well described by a nonlinear elasticity theory. And the important thing of those effects is that they have been observed to have sensitivity to the presence of imperfections or cracks or microcracks of different sizes in both cases, in the stress dependency and time dependency. So what is the conclusion of this is that then there is a way for us to measure the effect of microstructures in concrete structures. So we may have wave-field-based microstructurally sensitive measurements if we analyze the evolutive feature of elastic properties as a function of different factors, like stress and time. Now, many of the pioneering observations have been carried out under laboratory experiments or laboratory conditions. That means that they have control over temperature, humidity, and also a very fine control on the external forces that we apply to the material. Those in very small concrete specimens. And the promising application to large scale field condition concrete structure remains to be investigated. And this is where the importance of this work comes to the fore. So in this work, we aim to perform small scale imperfection assessment using concrete's nonlinear elastic behavior. And to do so, this structure is the perfect candidate. So this is the blade structure. The blade structure is a 24 meter long reinforced concrete test bridge that is located at BAM facilities. And the features of this structure makes it suitable for this experiment because this is equipped with a pretension system that essentially allows us to compress the structure in the longitudinal direction in a very controlled manner. We use this pre-stressing system to compress the structure at 5 different compressive forces in a decompression and decompressive and compressive stages. Besides that, we superimpose the effect of dynamic excitations by hitting the structure 3 times at every compressive force in this span of the bridge, that is the north span, and 3 times in the south span of the bridge. Again, just to investigate the effect of dynamic excitations superposed to static conditions. During the experiment, we recorded information at different time scales. We recorded information at low frequencies using this non-conventional equipment, that is 6-component equipment. Those record acceleration in 3 components and angular velocity with 3 more components. We also use conventional seismic equipment. This is vertical geophones of 4.5 hertz of natural frequency. So those are the geophones that are conventionally used for seismic exploration. And we also recorded information at very, very small scales, small time scales, by using 4 pairs of embedded ultrasound transducers that are, in the structure, within the structure, and are placed there, as you can observe, 2 of them in the north span and 2 of them in the south span. So this is the information that we recorded, and this gives us the opportunity to analyze these elastic effects at different scales. In one hand, we have the investigations on the material scale. On the other hand, we have investigations on the structural scale. So that brings me to the structure of this work. So in the part 1 of this work, we are going to investigate the feasibility of induced nonlinear elastic behavior in a controlled manner. And we want to check if this nonlinear elastic behavior saves a relationship with the structure's integrity. To do so, we introduce the concept of the cooperative analysis. What is the cooperative analysis is essentially mixing the benefits of the standardized techniques, as the ultrasound pulse velocity is, and the wave field-based microstructural sensitive measurements that we can observe with the acoustic effect and slow dynamics in a joint manner, and then investigate if, from the perspective of the linear elasticity, again by means of the ultrasound pulse velocity, classical nonlinear elasticity using the acoustic effect, and non-classical nonlinear elasticity using the slow dynamics, we can then obtain a more complete description on what is the integrity level of the structure, and also adding some information about the microstructural description that, is the result of such integrity level. And hopefully we can have as well insights on how a low integrity level look like and what is the microstructural description of it. And now it's the application of the cooperative analysis. Now the concept that I explained to you, we apply, and those are the results that we obtain. So first of all, let's analyze what happens with the ultrasound pulse velocity. The ultrasound pulse velocity then investigates the wave velocity that happens in the 4 different locations. We have 2 measurements in the south span and 2 more in the north span, and this is how it looks like. Broadly speaking, we can say that from the perspective of some of the standards, the ultrasound pulse velocity is high, and it corresponds to good quality concrete. But still, we can observe some subtle differences between north and south. And if we were asked to draw the line between high and low integrity, this is the way it looks like. In the north span, we have low integrity level, and in the south span, high integrity level. Now let's see what is the perspective of acoustoelasticity. Just to remember, acoustoelasticity is a linear effect that happens as a function of stress. So in the vertical axis, you have relative velocity changes. Those are relative to a reference state. In this case, the reference state is the beginning of the experiment, and this is the way it looks like. So at the beginning of the experiment, we observe no velocity changes, and as long as we decrease the compression on the bridge, we can observe a decrement in the wave velocities. This is the linear model that fits the measurements. This is when we decompress the structure, and this is what happens when we compress the structure again. Those observations correspond to the south right side, so that one right here. And just to better describe what is happening here, we can obtain the slope that is called acoustoelastic constant, and we have 2 slopes, one for decompression and one more for compression. This is the way it looks like, and when we compare the measurements with the 3 remaining places, this is the way it looks like. So again, we can observe that this acoustoelastic effect is happening strongly in this part of the bridge, and we can associate this effect to the action of tensile microstructures that are activated as long as we change the compressive force on the bridge. So yeah, with this we can be sure, we can validate that we can induce acoustoelastic effect. That means stress-dependent effects in concrete, in field condition, concrete structures, and still apparently there is a relationship with integrity level. Now it's the time for slow dynamics. So slow dynamics again is this coherent evolution of elastic properties as a function of time, and this is what we obtain. What you're about to see is how the elastic properties evolve as a function of time. This is what happens when we start recording, when we estimate the relative velocity changes just after changing the compressive force of the bridge. What happens here is the effect of the vertical impulsive source, the impulsive sources that we superpose to the static effects. So this coherent evolution happens when the structure is perturbed. And then again, you can see the velocity drop and the subsequent recovery process for 5 minutes. After 5 minutes, we hit the structure the second time, and finally, we did it in a third time. So what we did here is, first of all, this dataset corresponds to the information recorded in the south right side at this specific compressive force. And what we did here is we wanted to compare what is the similarity of the three relaxation processes. We superposed them. And then we estimated what is the velocity drop at the second 15, just to have it as a proxy for damage, for the process of damage. And this measurement corresponds to this specific compressive force. And this is in the vertical axis, the relative velocity change. Again, we have measurements at 8 different compressive forces. This is the way it looks like. But to make sense on this data, we only consider the minimum and maximum observed in the decompression and the minimum and maximum observed in the compressive force. This is the way it looks like for the south right side, which is exactly here. And this is how this analysis results for the 4 different locations. Again, we can see that not only for the magnitude, but also for the variability, that in specific places in the bridge, we have more strongly the effect of transient microstructures that happen when we excite the concrete structure with the vertical impulsive source. So yes, here we can be sure that we can analyze the slow dynamics effect. We can induce it and we can make sense and relate it to the integrity level. Now, what happens with the cooperative analysis? Cooperative analysis then is salient when we perform this joint interpretation of the 3 different regimes. That means mixing the information of linear elasticity, classical nonlinear elasticity, and non-classical nonlinear elasticity. Let's analyze it in this way. So here we analyze the results of ultrasound pulse velocity and acoustoelastic effect. So here we can identify 2 different groups. The first one corresponds to high integrity level and low values of acoustoelastic effect. That means low number density of tensile microstructures. On the other hand, we observe low ultrasound pulse velocities and high variability and high magnitudes of acoustoelastic effect. That means high density of tensile microstructures happening in that span of the bridge, which is, again, the north span. What happens if we combine the information of ultrasound pulse velocity and slow dynamics is this guy here. So here you can see, again, the information grouped in 2 main groups. The first one corresponds to high ultrasound pulse velocity and low variability of velocity drops. That means low density of transient microstructures. On the other hand, we have high density of transient microstructures. That means low integrity level and high variability. And finally, we can analyze this plane bounded by acoustoelastic effect and velocity drops. This is a bit more confusing, but still we can identify sort of this group here that corresponds to low density of tensile and transient microstructures together. And this guy here corresponds to high density of tensile and transient microstructures. So then this concept that we describe in this way can be transformed in this one, where we can find the information here that corresponds to high integrity level and low density of transient microstructures and tensile microstructures, and this guy here that corresponds to low integrity level and tensile and transient microstructures in a more present, in the structure. So the conclusion here is that still we can observe the sort of healthy material condensed in a specific region, whereas the part of the bridge that is to some extent less, that has a low integrity level, is more spread, it is more variable, let's say. The conclusion of this part 1 is that, all right, we wanted to see if we can induce nonlinear elastic behavior in concrete. We can, and is there any relationship between those measurements that we obtain and the structure's integrity? Apparently, yes. The cooperative analysis provide perfect description between the integrity level and the microstructures responsible for such integrity level. This is what is the part 1 of this thesis that is condensed in this publication that was recently published in the Journal of Non-Destructive Evaluation. In the part 2, we are going deeper into these time-dependent effects. We are analyzing how time dependency is happening in terms of velocity and attenuation. Let's start with time-dependent effects in terms of velocity. So maybe you recall this plot here where we only obtain information that corresponds to this specific part, essentially. We only extract this small bit of information, but there is a lot of things happening there, and we want to extract this information, not only this small portion. That's why the solution that we found is to essentially model what is happening here. And to do so, we have to identify the different elements that are happening in those measurements. So those are here. So this is the same data set in a plot in a different way. And we are identifying the different components of those observed here. So the first one is this sort of logarithmic processes happening. We have 3 of them that corresponds to the slow dynamics effects. The slow dynamic effect has been widely analyzed. And there's a lot of models that try to reproduce this phenomenon as a function of different variables. In this case, we are using this model developed by Snyder and Schanfelder in 2017, where we went to investigate what is the amplitude, so the velocity drop of those measurements that happen at different time scales, with those representative as the minimum and maximum time scales. So this is the first component of those measurements. The second component is this sort of non-stationary linear effect that is evolving through the time in a linear way. And we aim to obtain what is the slope of this linear effect. The third component is then the remaining effect of the first hammer hit. So whatever is not yet relaxed, has an effect in the second relaxation process. So we are compensating this relaxation process with this with this function. And therefore, we also have the remaining effect of the vertical impulsive source, number 2, acting in the third one. So yes, those are the 4 elements that we use to model the observations that we have. And if we assume a linear combination of all of them, of course, we can obtain a pretty much well-behaved model that is able to reproduce the measurements that we obtain. And the cool thing is that this small set corresponds to just a small portion of the experiment. This is one place at this specific compressive force, but we have 4 places. And in general, the model is able to reproduce the time-dependent relative velocity changes, no matter the integrity level of the material and no matter the compressive force. So with a model that is function of 4 different variables, we are able to reproduce time-dependent effects. But what is the model telling to us? Indeed, we can say a lot of things, but the crucial part that I want to address in this presentation is what is happening in terms of instantaneous softening, or why it is important. Well, maybe you can recall that a slow dynamics effect is sensible to microimperfections or heterogeneity level. Well, it turns out that it is affected by many more factors. What you have here is what is this softening process. In the vertical axis is the relative velocity change, so the softening. In the horizontal axis, you have the compressive force, and the different colors correspond to different places in the bridge. In a general way, we can say that softening is happening more strongly in the north side of the bridge and is happening less in the south side. But also, we can notice that the south side softens symmetrically under decompression and compression. This is also interesting because this gives us information about how the kinematic damage is happening in concrete at different integrity levels. And in the north span, where the structure softens more, this is happening mostly asymmetrically. So yes, we have more insights about what is happening in terms of damage kinematics in concrete of low integrity level. So yes, the points that I want to mention here is that instantaneous softening not only depend on the integrity level, but also depend on the compressive force and on the force rate, so the force that precedes the compressive state of the bridge. Now it is time to analyze the time-dependent effects, so attenuation, what is happening in terms of energy content on the waves. And this is as well quite interesting. Why? So we have those recordings again. You've seen this plot many times. This is how it looks like in low integrity level and high integrity level. What is interesting here is that if we analyze the energy content of the waves, we can have pretty much a similar shape in terms of relaxation process for low integrity and high integrity. What this plot suggests is that the slow dynamic process that happens in concrete is not only the result of changes in the elastic properties, but also changes in terms of dissipative processes. So energy is also deformed by, energy is also deformed as a function of time. So we observe here elastic processes happening simultaneously to dissipative processes. So this is interesting. This is interesting because there is more information about what is the nature of the microstructures, and those microstructures, suggest that the void volume is changing as a function of time. That suggests maybe the action of opening and closing microcracks in these slow dynamics effects. Again, we have those measurements in the place with relative high integrity level and the one with low integrity level. And those recordings of energy content are happening as well, no matter the integrity level and no matter the compressive force. We observe still relaxation processes using energy content, the energy information, so attenuation. So to conclude this part two, the time-dependent velocity can be modeled using the standard slow dynamic models. And those are crucial to reproduce our observations. Why is this relevant? Well, because those models have been used to reproduce results of still slow dynamic processes happening at very different spatial scales. So those measurements correspond to rock sample, like a very small rock sample, where we observe still slow dynamics happening. And those observations here correspond to the Earth scale. So what happens after the action of an earthquake? What it's telling to us is that the measurements that we're observing here contribute to expand the landscape of observations of slow dynamics in composite materials. So slow dynamics is, ubiquity in complex materials, not only in sampling rock samples, not only in Earth scale, but also in concrete structures. And in terms of attenuation, we observe time-dependent elastic and dissipative microstructures, again, that give us more certainty that what we are observing here is the action of rearrangement of grains, but also the opening and closing of voids, void volumes in the structure. And this is a paper in preparation. And finally, we can go to the structural scale investigation. And this is about if we can use the conventional sensors to sense the effect of small imperfections that we obtained or that we identified using ultrasound equipment. So in this case, we are no longer using waves that travel from the source to the receiver. We are changing the nature of this of those processes. Instead, we're analyzing stationary waves, so those waves that are trapped in the bridge, and how the velocity of the vertical oscillation changes as long as we reduce the compressive force again. So we are aiming to investigate how the velocity changes as a function of stress. So to do this analysis, we're going to use the information that we recorded with vertical geophones, the conventional equipment that is continuous recording along the whole experiment. And if we use this information and analyze it in the frequency regime, this is what we observe. So we observe 4 different representative peaks in the frequency domain, and those are referred to the fundamental first, second, and third mode. Those were identified by DAWO and collaborators in the frame of the GEOTO project. So for this analysis, I'm going to use only the fundamental mode. And again, what we are doing here is analyzing how this velocity of the fundamental oscillation changes from this, from the beginning of the experiment to this stage of the experiment, and how it looks like in the whole array, so the 12 geophones deployed. And this is how it looks like. What you're observing here is the velocity change as a function of, the velocity change estimated in the 12 different geophones. So in general, what we can observe here is that the velocity is changing differently in the south and north span. It is happening strongly in the north span. The color represents the quality of the measurement, which is pretty good. And the variability is represented by the vertical red bars. So yeah, at this point, we can observe that changes in the velocity of vertical oscillation are happening more in the north span, where we identify this low integrity level on the bridge. But then what happens if we analyze only the information recorded in the geophone tree as a function of all the compressive forces? And this is what happens. So maybe you can recall that for body waves, the high frequency analysis, this change as a function of stress happened linear as the way we observe here. But then what happens if we analyze this information as a function of the 12 geophones? And this is what happens. So essentially, we are identifying this acoustoelastic effect using a different type of waves. So in order to make sense on those observations, we are getting the slope of the linear models, and this is what you are observing here. So those are the slopes obtained for the compressive stage, and broadly speaking, it is still a bit unclear, but to some extent we can observe that the acoustoelastic effect is lower in the south span of the ridge than in the north span, and this is what happens when we compress the structure again. This information is still to some extent not clear, but we have certainty that this is still sensitive enough to observe the effect of small imperfections. Yeah, why? Because we observed that also in this plot, the effect of the vertical pillars that, yeah, to some extent change the behavior of the acoustoelastic effect. So yeah, the main idea of this third part of this third chapter was if we can sense the small scale imperfections with more conventional vibration sensors. Yes, we can use standing waves to analyze this nonlinear elastic effect. And maybe, again, you can remember that similar measurements were obtained using high frequency equipment. And this is also interesting because now we can see that this effect is present no matter the type of waves that we're using. And yeah, it is happening most likely due to changes in the elastic properties of the material. The second point is that conventional seismometers and accelerometers might be sensible to small imperfections. And those equipments are like, yeah, conventional geophones. And we can see that in this plot where we have different behaviors in relative velocity changes in the north span and south span of the bridge. The general conclusions of this work, then let's retake the research question if we can find practical ways to use mechanical waves to assess the effect of small scale imperfections in situ concrete structures. So yeah, in the first part, we observed that there is a way to improve the current non-destructive testing techniques with microstructural sensitive measurements. The microstructures that we identify in the first part have a dissipative and elastic nature. So we can suggest to some extent what is the nature of the transient and tensile microstructures that we are observing. And finally, at the structural scale, we can observe that using conventional sensors, we might be able to identify the effect of those small imperfections or small microcracks in a structural scale. And this information may be relevant for future structural pathologies in civil structures. Yeah, with this slide, I conclude my presentation. I thank you for your attention.